Okay, exercise 8.8, the composite function rule. A composite function is made up of two or more other functions, okay? In 2-unit, we only do it with two other functions. In 3-unit, we may do it with three functions. For example, if I've got y equals 3x squared minus 4 all to the power of 5, you normally would have seen this as something to the power of 5, but this, you normally would have seen it as x to the power of 5 before, right? But now you've got an actual another function in here where the x are what was. So what we've got, if you see something like y equals 3x squared minus 4 all to the power of 5, it's made up of the function y equals something to the power of 5. I've called all of this u. So it's made up of y equals u to the 5, where u is 3x squared minus 4. See, with this, you've got to do a double differentiation. You've got to pretend this is just one pronumeral like u to the power of 5, differentiate that, but you've also got to differentiate what's inside, okay? Now, I don't use this composite function rule. What I'll do on the next page, I do it another way, and I prefer to do it that second method, but I will show you, write this out because you need to know this method because we use this method a lot in 3-unit. Okay, so in 3-unit, you'll have this times that times another thing. So it's actually good to know this method. Look, I prefer the next method I'm going to show you. It's exactly the same thing. It's just written a different way. Then you don't have to learn the rule. It's just more a common sense method, the next method that I will show you. So when you've got, yes, you write this down. So if y is 3x squared minus 4 all to the power of 5, it's something to the power of 5, but that u is actually made up of x's as well. There's another function in that. So to differentiate this function, we use the following. dy dx equals dy du times du dx. Now, why does that work? Girls, if you're multiplying fractions, what would happen with the two du's? They would cancel and leave what? Yeah, because so dy du, I've started with dy dx, girls. So if my function is y equals 3x squared minus 4 to the power of 5, does it make sense that you're doing dy dx? Dy dx, yes. But the problem is you don't just have one x to the power of 5, you've got this complicated function to the power of 5. So the way we do it is, yes, we want to find dy dx, but to do that, if we let this equal u, we do dy du times du dx, in knowing that the du's will cancel. And I'll show you that over here. dy dx is dy du times du dx. If I cancel the du's and put ones in their place, I get dy dx. Does that make sense? So this is how it works. So this is my question. This is what I do. Let u, okay, do you have all that top bit? So we're going to use this rule. Dy dx is what we want to find because the function, we have y as a function of x. So we let u equal this extra bit in here. So u is 3x squared minus 4. And it would make sense to do what? Du dx now. Du dx is what? 3 times 2x, which is 6x. Now, our original, so stop there. Our original function, we're letting u equal that. So du dx is that. Because we let u equal that, my original function is u to the power of 5. Does that make sense? If u equals that, isn't my original function u to the power of 5? So therefore, if I want to differentiate this, what do I do? dy du. dy du is, this is a normal x to the n. What do? 5u to the 4. So I've got, okay, sorry girls. So girls, here's my original function. The first bit is to let u equal 3x squared minus 4. So therefore du dx is 6x. But because u is equal to 3x squared minus 4, the original function is y equals u to the 5. So now I can do dy du. So now I want dy dx, but don't I want dy dx? So dy dx will be dy du, because see the dy is on the top, the dy has to be on top here. And I need the dx on the bottom because the dx is on the bottom. And that du and this du will cancel. So it's dy du times du dx. Now what's dy du? Now I don't like this method. Let's go. 5u4 times du dx is 6x. Now We're nearly done. Now you've got to substitute back in what u is. 5. I'm never going to use this method again. Bracket 3x squared minus 4 to the 4 times. Why am I putting the u back in? Because I'm trying to differentiate this and my answer needs x's, not u's. So I've got 5, 3x squared minus 4 to the power of 4 because I'm replacing what the u is, times 6x, which is 30x bracket 3x squared minus 4 to the power of 4. Now you can see why I don't like this method. It's not that hard. No, it's done. I'm going to show you my method, the one I like. That's the answer. No, because you would never expand something to the power of 4. You'd be there for 10 minutes. Okay? No, what we're going to be doing when we do product rule, quotient rule and all that a bit later, tomorrow, and some of it today, we're just going to leave it like that. It's better to leave it like that. Now I'm going to show you the easier way of doing this question. The easier way. We'll do one more for practice soon, but I'm going to show you the other way. Have you got this down, girls? All right. My way is like, well, it's not my way. It's used as well. Now, the common sense method is this. Girls, isn't this what you are used to seeing? Y equals x to the n, dy dx is bring the n to the front, write the x down, drop a power. But now our questions are different. We've got y equals some function of x to the n, not just x to the n. So we follow the rule. What would the rule be? Bring the n to the front, pretend that's an x. Then you write down what's here, and then what do? Drop this. Now, but because this is a function and not just an x, you just differentiate it. See, because you're differentiating the main thing, but because this can be differentiated as well, you then times the derivative of what's inside. Now, I'll give you the same example. So, it makes sense. Bring that to the front, write this out, drop this down by 1, times, because this is not just an x, just differentiate what's inside. So, I'll do some examples with that. The same example as what we had before. So, I prefer this a lot better. Yep. Is that what they call it? Yeah. So, if y is 3x squared minus 4 to the power of 5, so what do? Dy dx. So, girls, it doesn't involve substitution. You don't have to let u equal that, differentiate that, substitute the u back in. It's just, all right, it's something to the power of 5. What does it make sense to do? Bring the 5 to the front, write this out, and put the 4 there. That's what you're used to doing, but I don't just have an x here, I've got a function, so differentiate what's inside. That's it. One step. Bit better than the other one, isn't it? So girls, it's something to the power of 5. So you bring the 5 to the front, write this out, drop the power of 4, which is what you've used to be. This is just doing this. So bring the n to the front, write it out, drop it down by a power of 1, which is what you're used to doing. But because you don't just have an x here, you've got a function, you differentiate what's inside. Times the derivative of what's inside. Why would you just leave that like that? You've got to differentiate that as well because you're trying to differentiate the whole thing. So we've got 30x bracket 3x squared minus 4 to the power of 4. It's a lot quicker. Right, we'll do some more examples. So much easier. And it makes sense. And it's going to work with logs, with exponential functions, with all these other functions that we're going to do. I'll just do some examples from their examples because they use the composite function rule. I just use this chain rule. So, no. So this one, girls, just use that chain rule, common sense method. What do? Something to the power of 7. 7 bracket 5x plus 4, drop this down, and then differentiate what's inside. 7 times 5 is 35, bracket 5x plus 4 to the power of 6. Isn't that much quicker than going let u equal 5x plus 4? Du dx is, y is u to the 7, dy du is, dy dx is dy du times du dx, substitute it, replace the u back. Why would you do all that? You just do this. Do the normal differentiation times, because this is not just an x, you've got to differentiate what's inside. Okay?
Will they ever tell us to use like the best method?
We'll use it in 3 unit, so don't worry. You'll get plenty of practice with it. Here's another example. I'll call that example 1. This is now example 2, even though the other one was 1. Y equals 3x squared plus 2x minus 1 to the power of 9. dy dx is 9, bracket, write it out, times, it's not just an x, so I have to differentiate what's inside. 6x plus 2. Be careful, can I put that in brackets because it's more than one term? So it'll be 9 times, yeah, you can probably just keep it like this. Or you can expand. Does that make sense? Or you can expand it to 54x plus 18, bracket, 3x squared plus 2x minus 1 to the power of 8. So girls, I prefer the first one. It's a simpler form. I wouldn't expand it. Okay, and someone just check the back and see how it's written. All right, which one? This is exercise,
The yellow tab at the top of my book.
I'll just pause for a sec. So girls, leave your answer like this in fully factorized form. I wouldn't expand like I did there, okay? All right, next question. Okay, ready? Example 3, differentiate this. Y equals the square root of 3 minus x. Girls, it doesn't look like something we can differentiate, so we change the way it looks. 3 minus x to the half. So do the same rule. dy dx is, bring the half to the front, 3 minus x to the negative half times, differentiate what's inside because it's not just an x, differentiate 3 and you get 0, differentiate negative x, negative 1. Good. So 2 times negative 1 is a negative a half. Now instead of writing this with negative a half, you write it on the denominator with a positive half. Does that make sense? A half times negative 1 is negative a half. This 3 minus x to the negative a half would be on the numerator. It's 3 minus x to the positive half on the denominator. The question was not written with powers of a half. What do? What do I change this power of a half to? Now, see how it's of the same format as the question. So girls, I don't want to see the composite function rule or whatever it's called. Let's use this. All right, we've got some more here. Let's do this one. Do you want to, we can practice one more of the other method as well. Oh, before I do this question, so this one, what are you going to do?
Can we bring it up?
Yep, you're going to bring it up. And how are you going to write it?
One bracket.
One bracket's not needed, so I can just 6x plus 1 to the negative 2. You don't need the 1 out the front. Does it make sense? Because it's not going to change anything. So dy dx is, what do you do?
Negative 2.
At the front, bracket, 6x plus 1
Negative 3.
times, differentiate what's inside, girls. You can't just ignore the fact that there's a function in there. It has to be differentiated, times 6. Now what do I do?
Negative 12.
Negative 12, yeah, 6x plus 1 to the negative 3, but we don't write it like that. Negative 12 stays at the top.
At the bottom. And
6x plus 1 cubed is on the bottom. Yep. So it's quick, isn't it? And it makes sense. Just follow your normal rule, but you happen to have a function in here, so just differentiate it. Otherwise, you're not differentiating the whole thing. Okay? So that's that. I'll just choose. All right, I'll just choose 1 or 2. All right, I'll just do another one. Ready? Can I get rid of that? Because we're going to do the quotient, the product rule in a minute. This one is easy. Easy, easy. This one's easy. All right. I might do I'm going to do question from the exercise 1. Y. Differentiate this. You're doing them all because it's good practice and they're quick. Okay, let's go. Differentiate that. Y equals 1 over the 4th root of, that little 4's in front there. 1 over the 4th root of 7 minus x to the power of 5. Let's work with this bottom, with the denominator.
X, 5 and 4.
That's right.
Wait, is that the 4th root? Or is that
The 4th root. It's a 4th root. 4th root of 7 minus x to the power of 5. So it's 7 minus x to the 5 on 4. Don't want it on the denominator. 7 minus x to the 5 on 4. That's what y is. Do not write dy dx yet. You haven't done it yet. You've just changed the way that y looks into a format that can be differentiated. So now what do we do? Dy dx is... Now we do our normal thing. Bring the power to the front, write it out, drop it by 1. If there's something that can be differentiated inside, you differentiate it. So it's negative 5 over 4. Write it out. To the drop this. What? This is negative 1 1/4 minus 1.
Negative 9 on 4.
Yes, it is. Negative 9 on 4 because it's negative 1 1/4 minus 1. It's negative 2 1/4. Times, differentiate what's inside. Yeah, if you differentiate 7, you get 0. If you differentiate negative x, girls, that's negative 9 on 4. Don't put negative 1/4 because I was going to. All right, times, differentiate what's inside, you get negative 1 because if you differentiate 7, you get 0. If you differentiate negative 1x, you get negative 1. So what do we do now? Negative 5 on 4 times negative 1 is 5 on 4. Do you want to write this down on the denominator? 7 minus x to the positive 9 on 4, which is 5 on 4, the 4th root of... So, get rid of the negative power by putting this on the denominator. The 5 and the 4 stay in the same place. Negative times negative is positive. 7 minus x all to the power of 9. Okay. That's that. And it has to be in the same format as the question. No negative powers, no fractional indices. Okay? Now, we're going to do one question from... Actually, no, I'll get you to do all those others because it's good practice for you. So what you'll be doing for homework so far is exercise 8.8. You can probably just do every second question from question 1, not every one. They're very repetitive. Oh, maybe just do question 1, every second question, and you can start. Do you want to start from A or B?
We'll go A, C.
That should, or what you do, you pick the ones that look hard, yeah, A, C, E, etc. Okay, and questions 2 through to 6, they're the worded problem ones, all right? So there's only 5 worded problem ones about equation of tangents and stuff like that, which you need to practice, and every second question of that. Shh, girls, I'm doing product. Doing one more example, but using the dy dx equals dy du times du dx method. So we will do this question here. So differentiate, one sec, y equals 3x minus 1 to the power of a half using that method. So what do? Let u equal 3x minus 1. So girls, you may decide to do 2 columns, might be the better way as well. So what would you do next? Du x is, if u is a function of x, you do du dx. If there was a y here, you do dy dx. So du dx is 3. Now we know that our original function is that, So there, and y equals what to the, what's this? U to the half. So dy du is u to the minus half, which is, you may as well change the way it looks. Instead of writing u to the negative half on the numerator, you put it as u to the positive half on the denominator, don't you?
Yeah.
Girls, that u to the negative half is on the numerator because it's not over. So now you write that as 1 over 2 what? Root u. Now, so dy, I know I'm off the page. So dy dx is dy du times du dx. What you might want to do is, why don't we do this substitution of what u is back here? Root what?
3x
Yeah, so let's put it in 3x minus 1. Got it? So what's dy du? This 1 over 2 root times du dx is 3. So it just becomes 3 on 2 root 3x minus 1. So you would never, by choice, do this method. Never, ever, ever. The other thing is so much easier. You're still just using the one rule of differentiation, but there happens to be a function there. Of course, it makes sense to differentiate that function. Because girls, if there was just an x there and you differentiate, like if you think of that rule, and if I'm differentiating this and I want to use that chain rule, isn't it 7x to the 6 times differentiate the x, and what do you get? Same rule. Do you see that? So that's using that new rule that we've learnt. 7x to the 6, if you differentiate the x, you get 1. But we don't do that when we've just got x to the n. But see how you get the same thing anyway? All right? All right.